who is going to talk about transfer learning. He will focus on two methods that we implemented here at Taboola Algorithms Group, and we will also show how we took it to production. So feel free to use the chat to ask questions. And also, I remind you, we are going to have breakout rooms after the presentation for about 10-15 minutes until 5. So the rooms will, of course, be smaller with a representative from Taboola in each room. So you can also ask your questions there. Petros, can you hear me?
Yes.
Okay.
So thanks everybody for joining. Let me share my screen and I will introduce myself. I will start. You can see it?
Yes, we can see it. It's not on present mode yet. Okay. Great.
Okay, good. So hi everyone. My name is Petros Katsileros. I'm an algorithm engineer in Taboola's Algo Group, and specifically I'm a member of Deep Labs team inside Taboola. And as you know, we will talk about knowledge distillation. So at first, we will let's see an overview of this presentation. We will start with a very practical example, take an intuition about why we need knowledge distillation in machine learning and what it actually is. We will see some relevant techniques that exist and we have already implemented and we are currently using in our system. We will compare these two methods and we will see the pros and cons for each one. Finally, we will see what is the infrastructure to be able to handle such cases and such complex architectures in production systems. And then we will see what are the benefits that we have using these techniques. And then we will wrap up everything with some conclusions. So before I start with the technical stuff, I want to make an introduction in order for everyone to have a clear view of what it is and why we need to apply it in machine learning. So we'll start with an example from our real lives. And we all know that when we get born, we have very little knowledge about what is going on around us. So we have our parents to help us in our everyday lives, and they give us guidance in order to move forward. Then we go to school, we have our teachers, and specifically we have different teachers. We have the math teacher, we have the history teacher, and they always give us more knowledge and more guidance, and we accumulate this knowledge in order to move forward. So later on, we go to the university, and again, we have the professors, we have the books, we have the internet. So the main point to keep from this is that constantly, while we're moving forward and we're developing ourselves, we accumulate previous knowledge that we have gained, and we use it in our everyday lives. And also, it's very important that we take outsource information from other people that we trust and that are smarter than us, in order to become smarter and smarter. So now that we have a very brief understanding of what we are talking when we mean about transfer knowledge and knowledge distillation, let's see how this concept applies in the machine learning domain. So the main thing that we want to achieve is, as previously mentioned, we want to leverage knowledge between different models. And what we mean by different models, we mean that we may have big capacity models transfer knowledge to lower capacity models, and also exploit big data sets in order to solve problems in small data sets. I will show you to the next slide exactly what we mean with this setup. But for now, let's see a very brief overview for a specific machine learning setup. So for example, we have the dataset 1 and we train a machine learning model 1 in the traditional machine learning setup. And then we have a dataset 2 and we retrain another machine learning model 2. So in the transfer learning domain, we say, okay, we will train the machine learning model on dataset 1, and somehow we want to pass this knowledge to the machine learning model 2 while it trains with the dataset 2. As I said, I will show you a very specific example to the next slide. For now, if someone wants to read more about it, the first paper about it is called Learning to Rank from the 1995 NIPS workshop. And also I have added a phrase from Ian Goodfellow's book that says that transfer learning is the situation where what has been learned in one setting is exploited to improve generalization in another setting. And I'm pretty sure you will understand what this phrase means in the next slides. So let's see a very practical example of a specific appliance of the transfer knowledge techniques. Say, for example, that we have the ImageNet. I'm pretty sure a lot of you will know this dataset. It's an image dataset with 1,000 classes, and we have trained a very big model on this dataset. The shape of the sizes of the shapes matters in this slide and in general in the whole presentation, which means that the bigger the dataset, the more the data, and the bigger the model, the more the parameters of the model. So, for example, we have trained this big model, which has learned to classify correctly 1,000 classes. But in the real world, we have another problem to solve. We have a very small data set with specific cars, and we want to deploy a very lightweight model on a mobile application. So in this case, at first, we don't have a lot of data to train our light model on the cars dataset. So we need somehow to exploit the big green dataset. And also, since it is a mobile application, we cannot have the big model deployed. So as you can see on the right side, we have a very lightweight model trained on a very small dataset. And for this reason, to have a very good performance, we have to somehow transfer the knowledge from left to right. From the left model, which is smarter and bigger, to the right model, which is smaller and specialized in a specific domain. So, is everyone with me until here?
Mm-hmm.
Yes.
Good. So let's continue with specific techniques now that we have the general knowledge of what we are talking about regarding the transfer knowledge. Let's see some machine learning techniques that we use and currently exist. The first technique that is the most common is the Warmstar technique. And again, I'm pretty sure a lot of you will be familiar with this technique. The main idea is that we want to leverage prior computations and not recompute them again. And by leveraging this thing, we reduce dramatically the total optimization process time. And I will show you on the right side how specifically we can achieve this. We can achieve it by starting with pretrained weights rather than random initialized weights for a specific network, which makes the optimization process much faster. So let's see an example with two neural networks. On this side, we have a specific dataset, the green one, with a specific network architecture. And on the right side, we have a smaller dataset, the red one, and again, one neural network with the same architecture as the left. So the main idea around the Wormstar is that we share some knowledge, as we saw earlier, and by sharing, we mean that we share specific layers of the network topology. In this situation, we copy layer 1 and layer 2 pre-trained variables or parameters, and we use them to start training with the red dataset. In general, in the Warmstar domain, we have two options with the shared layers. The first one is to freeze them, which means to not run any back propagation updates while training with the red dataset, or fine-tune them. By fine-tuning, we mean that we start updating the parameters normally as we do in a normal training for a network. Finally, we have the last layer, which in most cases we want to fine-tune it because, as we saw in the previous example, maybe the left network will output 1,000 classes, but the right one we want to just output one. So in general, we fine-tune almost always the last layer. So as you can see here, we share some model parameters, which is parameters of the layers, but we also have implicitly an enriched data corpus because we have learned some things in the green dataset, and we're able to pass somehow this knowledge in the red dataset. And in general, as we have seen in similar domains like image and text, we do this technique by leveraging very large deep learning models, especially in text and in image problems. So the Warmstar is good, it's very good, and it works really good in practice. But if we think of it, it's like copying one's brain to another person. And this is what people do. As we saw in the start of the presentation, as people, we accumulate knowledge while we move forward to our lives constantly, and not as a one-step procedure. So what if I told you that we can also have it in the machine learning domain? Like, don't copy the initialization of the model like we do in the Wormstar, but having a constantly accumulation of knowledge while training. It should be super powerful, right? Let's see a hypothetical scenario how we could do it. Please, if someone has any question, stop me. I want to be super clear of what is going on, but I think it's for now it's pretty simple idea. So let's see this hypothetical scenario. As we do as people, what if we could ask a smarter model to tell us how it thinks we should proceed with a specific example, like we ask our parents or our teachers, or we Google something or anything. And if we could do it, suppose that we get an answer, how could we use this knowledge? We as people, we take someone's opinion that we trust and we know that it's smarter than us, and we consider his opinion while we're proceeding forward. So can we do something similar, like take a supervision signal while we solve a specific problem in the machine learning domain? And if yes, how can we do it? Is it possible? So as you imagined, of course, it is possible, and there is a specific architecture for transfer knowledge. It's called student teacher, and if you let your imagination, I'm pretty sure you can imagine what is going on behind the scenes. But I will show you exactly here what this setup looks like. So in a typical machine learning setup, we have a model and we run a forward pass with a bunch of examples. We calculate a loss, for example, the cross entropy loss, and then we run back propagation. So with the student teacher setup, as we saw previous, we have the option to ask someone, a smarter model than us, hey, I have a specific example inside this batch. Can you tell me what's your estimation for this example? Like how you think I should proceed with it, what my gradient should be. And this model actually gives us an answer. And now we have to somehow use this answer in order to accumulate knowledge or perform better by solving this specific problem. So in the machine learning domain, the most common thing that we do, it's very simple, but super efficient and smart. It's to add it in our current loss calculation, like an extra term. It's the same way like adding a regularization in our current loss. So in this way, we say to the student model that, listen, you have to update your gradients given your estimation, but you have to follow very closely the teacher model, because you know he's good to answer you the question you asked him, and you trust him to give you estimation for the specific problem. So it's very similar to what we do in our real lives, and also it works pretty well in a machine learning domain, and we will see later why. So this is the only mathematical equation I have in the presentation. It's pretty straightforward. Let's see specifically how this loss has been calculated. We have two parts. The first part is actually the cross entropy loss of the student model, and actually is the cross entropy between the true labels and the estimations of our current model. And the second part is the cross entropy between the supervision signals, which is the SI, and the estimation of the student model, which actually says to the student model, listen, your estimations should follow your teacher because you trust it and you should follow his advice. It's super easy and super practical, and it works really nice in practice. So let's dive into to see this setup and to understand what is the difference from the Warmstar. given a specific neural network topology. So as we saw in the previous slide, the student takes supervision signals from the teacher by asking him questions. And actually, we use the answer of the teacher to regularize the student optimization loss. The main difference between this and the Warmstar is that we start with initialized weights, with random initialized weights, while in the Warmstar, we copied the pre-trained embeddings. So this idea is being distilled the knowledge in a neural network paper from Hinton in 2015. Anyone interested can read it. And let's see now what it looks like for a specific neural network example. Say again that we have this specific neural network. It's the teacher model. And from the other side, we have another model. So the difference here and what we should focus on is that the left neural network has different architecture from the right one. And this is why I have added these bounded boxes in order to make super clear that in this situation, the only way that the two models interact and the only way that the teacher passes knowledge to the student is by giving the supervision signal to the output of the student model. And as we saw in the previous slide, we actually add an extra loss term to the student loss model, which actually measures the similarity between the teacher and the student estimations. So we tell to the student, we have to just follow to your teacher. So is anything clear until now? Maybe any question?
Does it have to be cross entropy, or that can be also other losses of regression problems and not necessarily classification?
It can be any loss you want. The main point is that we add an extra term next to it, which says that, listen, you have to follow the estimations of your teacher. Okay?
Thanks.
Good. So, as we saw, the student model could be completely different architecture from the teacher model, and this is super, super important, as we will see later, especially in production systems, where so many people work on the system, and the system is vulnerable to break. And also, this gives us more flexibility, and we will see in more details why we have more flexibility with this architecture. So for now, to close the theoretical aspect between these two methods, let's make a simple comparison between them. So we saw that a main difference that these two approaches have is that the modular architecture in the Warmstar scenario should be almost the same, because actually we copy whole layers or embeddings or anything from one network and we copy it to the other. So the dimensionality should match, and the number of layers and the size, etc. While in the student teacher, we saw that the only way that these two models interact is by adding an extra term to the output of the network, so they can be completely different architectures. Another major difference is that the Warmstar scenario uses just the hard labels, which actually is the labels that we have for our dataset, while with the student teacher setup, we have an extra loss term, which actually uses an estimation of the teacher, which would be said like it's kind of soft labels. Finally, we have a better ability to transfer knowledge using the student-teacher approach, and we will understand it better later, where we will see how this architecture is being used in our production system. And after the experimentation we did, and after we tried both models, we saw that the student-teacher is a more powerful transfer knowledge scenario, which also brings Taboola more money, which means that it works better in production, which is very nice. So cool. We are aware of these two approaches. We have understand the technical details behind them. Now let's see how can we move to production with such systems, and why we want to consider the production. Because at Taboola we have a very big data and a very huge recommendation machine, which serves 500,000 requests per second, which means that we gather 60 terabytes per day, and we have a strong requirement for our models to serve with less than 20 milliseconds, which is a very strict requirement for production systems. And this whole infrastructure let us have 1.4 billion monthly unique users. And in order to serve this amount of traffic, we have 5,000 online deep learning containers. So as you understand, we're talking about a huge infrastructure and a very big system that needs a lot of engineering skills to have such complex scenarios like the Wormstar. And as we will see in the next slides, this requires a lot of sophisticated tools and setups and a lot of engineering effort to have a stable production system with these technologies. So let's start with the Warmstarter infrastructure. And I'm taking the opportunity here to introduce some of the technologies that we use. So say, for example, that we have the green dataset, and we want to train a specific model with this dataset. We use TensorFlow as the machine learning backend machine for our trainings. And while we're training, we always consistently dump logging information in the Elasticsearch because they are super important to monitor things and to know what is going on behind the scenes. When we finish with the training, we dump in Kubernetes the trained model. We deploy, the trained model to the Kubernetes, and we dump it in HDFS because maybe we want to load it, etc. So let's now move to the second model, to the red one, and we want to use the Warmstarter architecture. So in this case, while we start training the red model, we have to somehow copy the knowledge from the green one. So we go to HDFS, we know from Elasticsearch and all the logs where the model is located, which model to take, and of course, all this scheduling is becoming using Airflow, which is more complicated than we see here. So we load the pre-trained model, the green one, we copy its parameters in the red model, and we continue to train the second model. And again, we dump the logs in Elasticsearch, and we deploy it in Kubernetes while the training finishes. So if we're okay with this architecture, let's dive into a specific neural network architecture with this setup using the Warmstar. So specifically, we have the source and the target models to share the same architecture as we saw previous. The source and the target data are different, and we fine-tune the whole network. Like we don't freeze the shared layers, we fine-tune everything, and you will understand why we do it. So let's say that we have a specific dataset, the green one, and a specific network topology that we train on. And on the other side, we have another dataset, the red one. And I have added some colors here in order to show that we share actually all the layers of the network, and we run fine-tune this. It's pretty simplified here, what you can see, but in practice, this is what happens. Given that we have a lot data, as we saw in the previous slide, and we have rich information of data in both datasets, we don't want to only transfer the knowledge from the shared layers. So we have implemented an extension. It's a custom thing, and we have extended the classical Warmstar scenario, and we're able to somehow mix and match between the data of the two datasets. So in this scenario, we don't only pass the knowledge of the pre-trained parameters, but we also reuse some data, some rich data from the green dataset to the red dataset. And this plays a super crucial role, especially in our domain where we have so many embeddings from different data segments, and we want to mix and match between them. So what are the benefits of Taboola using the Wormstar? At first, we leveraged our rich data. We took some models and we trained them on some data groups with very rich information or with a lot of data. And we use these models to Warmstar other models trained of different data segments, which may have less data or lower quality data. Another very important thing is that we understood what is going on behind the scenes with our data. because with Warmstar, we saw that, okay, this data segment is able to transfer knowledge to this data segment, and it's a very nice intuition to understand what is going on with our real datasets. Then we have a faster go-to-production scheme, because as we saw, we can start with already pre-trained weights. So the optimization procedure is happening very fast. And we saw a big revenue increase by leveraging knowledge between different data segments and different models. So is anyone with me until here with the Wormstar?
Yep.
Good. So what about the student-teacher architecture, which we said at first that it's more efficient and we prefer to use it rather than the Wormstar? Let's see a typical setup with this thing, and we will understand why it's way more powerful than the classical Warmstar transfer learning technique. So in this scenario, our main focus is to have a very smart model, which means a model that is trained on a lot of data, more data than our current normal models, and then we have some other models, the student models, which are trained on our normal data set, let's say. And for now, the student and the teacher share the same architecture. So someone will ask me, okay, since again we have the same architecture, why don't you use Warmstar? I'm pretty sure you will get the idea behind it, and we'll see together why this setup is more flexible and a more advanced technique to pass knowledge between different models and different data segments. So let's say that we have a different data sets and number of data sets, and we combine them all together to a very special model, the teacher model. Then we have distinct other data sets, the red ones, and we have some other models trained on these data sets. But because we want to transfer knowledge between the teacher to these student models, we say, okay, you student model, you have to take the knowledge from this specific teacher. Of course, this setup is simplified a lot, and in practice, we can have a lot of different teachers and a lot of different models. So again, we have here a very big infrastructure with Airflow, which schedules everything, and a lot of Kubernetes containers. But this is the main idea, that we gather a lot of knowledge in a specific model, and this transfers the knowledge to separate student models. So why we say that this model is more powerful than the Warmstar? I will go back again to how people perform in real life. So let's say that yesterday we have learned something, for example, to walk, and today we want to learn how to run. So we don't have again today to learn how to walk. We want to start from the walking and then learn how to run. And this is exactly what we want to achieve with this setup, with the student-teacher architecture. We want to accumulate knowledge across time. So say that we are on time t, and we train a teacher model, the model 1, and we share its knowledge with the model 2, the student model. When we go to the t+1, as you can see, the second model becomes teacher for the third model. So what we learn on time t, we want to pass it to the third model, to the next timestamp. And this can be continue as we move forward to the time. But as we see with people, we want to not only use ourselves, our previous knowledge, in order to become better and better, but we also want to exploit different sources of teachers. So in practice, we have a more sophisticated setup like this one, where, for example, for the third model on t+1 time, we have 2 teachers, ourselves from the time t, and another model, another teacher model. So this is a more sophisticated scenario with multiple teacher models for a specific student. And also, we accumulate knowledge as we move forward the time. So what are the benefits of using this infrastructure and this technique? Our production system is way more robust, and it's more robust because we're able to have different architectures to share knowledge. We're not dependent on the same architecture as we were in Warmstar, which, trust me, it's super crucial when a lot of people are writing code on the same TensorFlow model and the model changes very rapidly. So again, without having the limitation of the same architecture, we can have very small student models in production, which will reduce dramatically the computation resources for the training time, and also it will reduce the latency while serving in production, which is super important. And finally, by testing this thing online, we saw more revenue than the Wormstar, which is a pretty cool thing. And as we saw in the last slide, with this setup, we can have more sophisticated transfer knowledge techniques, like using the previous student as current timestamp teachers, and also use multiple teachers for single models, which is a very powerful technique to mix and match between a lot of models and a lot of data. So let's have a summary about what we have learned regarding the knowledge distillation in the machine learning domain. So we got the intuition why we need it. We need it because we cannot have huge models in production, and in real problems, we may not have a lot of data or not rich information of data. We did an actual comparison between knowledge distillation methods that exists and we have currently used in our infrastructure, the Warmstar and the student-teacher approach. We saw the whole infrastructure that and the engineering effort that the production-ready system requires to handle such complex scenarios. And then we saw what a production system with this infrastructure is, and especially at scale with the numbers that we saw regarding Taboola's recommendation machine. And finally, we show that the huge benefits that we have, both in the flexibility of different setups and also in the revenue increase. So thank you. I hope you enjoyed it.